Today's practical is entitled the Paracetamol assay. So just a bit of background about paracetamol. It's a molecule of about 151 grams per mole. It's a commonly used analgesic and antipyretic drug, meaning that it is used to relieve pain and to reduce temperature. However, unlike drugs of a similar class, it has poor anti-inflammatory activity. Paracetamol poisoning is a common problem. A lot of people overdose with paracetamol in combination with alcohol, and therefore an assay is needed to determine the therapeutic and toxic concentrations and for monitoring as well post-administration. So a plasma concentration of paracetamol is determined by a colorimetric assay. The usual reagent that's used for this is something called trichloroacetic acid, because it removes plasma proteins from the sample. So normally plasma proteins will bind to paracetamol, so in order, and would interfere as well with the assay in determining paracetamol concentration in the plasma. So in order to get the free concentration, trichloroacetic acid is added to the sample, the plasma sample, to remove the plasma proteins in order to get the free concentration. So just to show you again, on the bottom right here, we have a concentration curve over time, over about 6 hours, of the plasma concentration of paracetamol, or acetaminophen as it's otherwise known as. And it compares two different routes of administration, the oral route and the IV or intravenous route. As you'll notice the difference between the two of them. For the intravenous route, the concentration increases immediately and reaches a peak almost immediately as well. Whereas for the oral dose, it takes a bit of time because it's being absorbed in the gastrointestinal tract, and then it slowly levels off. So we'll be doing something like this with a number of different samples. We'll be trying to measure the concentration of paracetamol in the plasma. And for the next practical then, we'll be doing the half-life. So we'll be generating a curve similar to this, whereby we measure the paracetamol concentration in several different samples. So in order to do that, like many of the other practicals we've done so far, we need to make up a stock solution. This will contain 100 milligrams of paracetamol in 100 mils, or a 1 mg per mil solution. As before, you'll need to make sure you vortex very well in distilled water in order to get it all dissolved. Don't forget again to transfer all the solution and all the washings from your beaker to the volumetric flask, and carefully make it up to the mark. So in this particular protocol, you need 2 sets of 9 Eppendorfs, 6 for the standards and 3 for the samples. So you'll each be given 1 sample, and you'll also have the neat and the 2 dilutions of that particular sample. So the first set of tubes, the first set of 9 tubes that you'll need, are for making up the standards and the samples prepared as 1 ml aliquots. Whereas the second set are the assay tubes. They're the mixtures of these standards and samples with the TCA, the trichloroacetic acid, with the sodium nitrite, and with the sodium hydroxide. So in order to do that, we need to pipette 100 microliters from set 1. So when you make up your 1 ml aliquots, you will take 100 microliters of those, transfer them into the second set of tubes, corresponding set of tubes, and put the first set out of the way. So make sure you don't mix them up, and the assay is done using the second set. So you have your 100 microliters in the second tube, and to that you'll add 1 ml of 3% trichloroacetic acid. Remember, this is used to precipitate any plasma proteins normally when you're doing the test. It has 300 microliters of sodium nitrite, which you vortex and leave for about 20 minutes. And finally, you add 50 microliters of 8 molar sodium hydroxide. So please be very careful in handling this. This is quite a concentrated and caustic solution, so 8 molar is very, very concentrated. And make sure as well when you're vortexing between your addition that you have the cap on the tube fully down. So you do this for all your standards and also for your unknowns. So you have your neat sample and then your 2 different dilutions. So after a bit of time, you'll develop a yellow color, hopefully. So make sure you check that you do have that deep yellow color in your tubes. And then finally, you transfer 200 microliters 4 times for each sample and for each standard to the 96 well plate. And you read your plate at 450 nanometers. So from the absorbance values, obviously you'll have to subtract the blank from your absorbances, get an average, and construct a standard curve with absorbance on the y-axis and the concentration on the x-axis. Get your best fit straight line through the origin and determine the concentration of your unknown. So using your neat, your two different dilutions, and don't forget to extrapolate using the original absorbance for the diluted unknowns, and then multiply it by the dilution factor. So if it's a 1 and 2, for example, that you use the absorbance that you get, go across on the graph to extrapolate the concentration, and then finally once you get that concentration you multiply the answer by 2, for example. At this stage you've done quite a number of practicals, and you should be improving your accuracy and precision in terms of your pipetting, you're making up your solution. So just very briefly I wanted to mention a few things that can go wrong, particularly with regards to making up the stock solution. Not weighing the compound accurately, not mixing properly, making up the standards from the stock as well can be an issue sometimes, not pipetting accurately and precisely, not vortexing between your first and second tubes, adding the chemicals to the wrong set of tubes, not vortexing after each of the steps, and not giving the full 20 minutes before adding the NaOH. So after you add the sodium nitrite, you should wait at least 20 minutes before you get the colour development. And then finally, not vortexing and mixing properly before you dispense the solution into the 96 well plate.